The function that you see in that paragraph, the position, the particle is traveling along the x-axis. So when we graph that parabola, we get that. That's not what the particle is doing. That just tells us the distance as time goes on. That at certain time t, there is a maximum x-coordinate. And then the x-coordinate starts to decrease. What is the particle doing? The particle is moving to the left. It gets to a maximum x position, and then it's moving back. So you're moving to the right and moving back to the left. And I know that because this is what the distance from the origin graph looks like. We still have the same position, velocity, and acceleration formulas that we had before. That when I go in this direction, I take the derivative. I take the derivative with respect to time to find the velocity and the acceleration vector. To go the other way, I'm going to integrate, again, with respect to time. Now I just have two problems to do in each one. And don't forget, we're always going to have the plus c when I integrate. Speed. When we have motion in one direction, speed was just the absolute value of velocity. With vectors, the absolute value of velocity looks like the length of the velocity vector. So the length of the velocity vector is just our Pythagorean theorem. All right, velocity, acceleration, and speed. So we want to generate a rectangular equation that describes the particle's motion. So the particle is moving in the plane. It's not just one direction, it's rectilinear motion that's called. That's why we're going to use RT for the position vector, because it's moving catawampus. And we've done this example twice. What's this graph going to look like? Talk with your partner, what's the graph going to look like, and how is it different than the way that you encountered it in pre-calc or trig? Go. Why are you talking about inverse? Yeah. So we kind of, in a sense, we switched x and y. And so there's a couple of differences. The unit circle has a radius of 1. We're going to get a circle here. What's the radius? 3. Why? The dilation in the horizontal direction is 3. The dilation in the vertical direction is 3. In a sense, we kind of did do an inverse. We switched cosine and sine. We're still graphing a circle. What impact does switching sine and cosine have? It does. It doesn't have an impact on the final product. It has an impact only when we consider time. Because on the unit circle, when it's cosine comma sine, cosine is decreasing in the first quadrant, sine is increasing in the first quadrant, so the graph looked like this. And it graphed counterclockwise. This one, we've switched x and y. The x-coordinate is going to be increasing, and the y-coordinate will be decreasing, so this one is going to graph in the other direction. And we'll see that when we graph it. There's one other difference between, so we got a larger radius, we are graphing it in the other orientation. There's one other subtle difference. What is it? What? What impact is that going to have? Dilation, which direction? Nope. That's the 3 in front. That's the 3 in front of the cosine, the j component. It's a time dilation, right? So that's a great question. Is it slower or faster? Well, now we've covered both bases. That's good. Can't be wrong now. How do you say slower? How do you say faster? How many aren't voting? Typical American. It is typical because it's about 70% of us. It is slower, right? Because I'm cutting the time in half. I have to have twice as large of a time value to get that same coordinate. So we have slowed it down. All right, so we've dilated time. Ooh, that's kind of fun to say. All right, so we're going to go ahead and figure out what that equation is. If we know the equation of a circle, we can kind of almost skip, and we know this is a circle, we can kind of skip right to the answer. If we don't, we'll have to do what we did previously. I'm going to say x equals the horizontal component of the vector, and y equals the vertical component of the vector. And we're going to eliminate the parameter. We've eliminated the parameter by solving for t equals and substituting in. We could do that. It's going to get really messy. So instead, we use a little trig identity. I'm going to divide both sides of the equal sign by 3. And then I'm going to square both sides. It's legal in 49 of the 50 states. On the left side, I get x squared over 3 squared plus y squared over 3 squared. On the right side, I get cosine squared t over 2, or sine squared t over 2 plus cosine squared t over 2. What does that equal? I know that cosine squared theta plus sine squared theta equals 1. But I don't have theta, but the argument is the same. Because the argument is the same, I can really just kind of consider this to be theta and this to be theta. Sine squared theta plus cosine squared theta does equal 1. So we get x squared plus y squared equals 9 times 1. And there's the equation of the circle. That's the circular path that this object, this particle, will follow. All right, the velocity vector. For the velocity vector, I'm just going to take the derivative of the position vector. So the velocity vector is equal to, I'm going to take the derivative of 3 sine t over 2 times I. Flashcard fact review and chain rule review. The derivative of the sine of something, or the derivative of a constant times a function, is the constant times the derivative of the function. The derivative of the sine of something is the cosine of the something times the derivative of the something. This is a vector, so I'm going to show that that's a vector by putting an I. The derivative of 3 cosine t over 2 is negative 3 cosine t over 2 times the derivative of t over 2. Yes. Times vector j. So there's our velocity vector. Our acceleration vector, lather, rinse, repeat. The acceleration vector is the derivative of the velocity vector. So it's going to be negative 3 halves sine of t over 2 times the derivative of t over 2, so I can make that 3/4. That's the horizontal component of the acceleration vector. So I'm going to multiply by I, by vector I, plus negative 3/4 cosine t over 2 times vector j. And there's the acceleration vector. So, velocity is still the derivative of position. I just have a horizontal component of the velocity and a vertical component. Acceleration is still the derivative of velocity. I just have to take the vertical and horizontal derivatives. Yay? And the speed. Speed is the square root of the horizontal component of the vector, of the velocity vector, plus the vertical component of the velocity vector squared, and there it is. Yes? The absolute value is going to come from the fact that I'm squaring each individual thing.
No, but like, can't you just do that?
No. I have, speed is the absolute value of velocity. The way that works with vectors, the absolute value of a vector is the length of the vector. And so you have to use Pythagorean. It's tied into the absolute value of a complex number. That's it. But wait, what follows is really satisfying. Like the pressure washer tick-tock. Okay, it's really satisfying. Here we go. I'm going to square each factor. Square each factor. Some of you have already leapt to the answer. What's my next step? It equals what? What's my next step? Okay, we're going to factor, right? So I'm going to factor out the 9/4, undistributed. What's in the parentheses? 1. So 1 times 9/4 is 9/4. The square root of 9/4 is 3/2. What do we know about the speed? It's constant. The speed, as we travel around, as we run laps around this circle, the speed is constant. I think we could also almost make a, because of the derivation that we just did, or the simplification that we just did, we could probably almost make a generalization. Yeah.
Why do we have an acceleration?
Right. The velocity is not constant, the speed is. Right. All right, so here we go. Turn the page. So we're going to graph that path. I think we already know the answer. Sorry for ruining it for you, but we're going to go ahead and make a TXY table. Substituting in 0 is pretty seems to be pretty natural to do. 0 divided by 2, when I substitute 0 in for t, is 0. Sine of 0 is, times 3 is, oh, I hope all the calculations are this easy. cosine of pi over 2, and I substitute, cosine of 0 over 2, and I substitute 0 in is 1. Cosine of 0 is 1. Times 3 is 3. What should I substitute in next? I could do 1, but I don't know the sine of 1/2. I know it's close to 1/2. But I don't know the cosine of 1/2. And I could do 2, because I got 2 divided by 2, but I don't even know what the sine of 1 is. Yeah, so sticking with numbers that have good trig values, because I forgot my calculator at home. Almost as bad as forgetting your track uniform at home when there's a track meet today. All right, so the sine of pi over 2, I'm going to substitute it in right here. Sine of pi over 2, 1 times 3 is 3, yay, unit circle. Cosine of pi over 2 is 0. And times 3 is 0. The next number I should substitute in? 2 pi. And when I substitute 2 pi into my position vector, I get 0. Cosine of 2 pi over 2 is cosine of pi, which is -1. -1 times 3 is -3. Substitute 3 pi in. And I think we're going to get -3. The sine of 3 pi over 2 is -1. So, if we were to graph this puppy, at time 0, I'm at the ordered pair 0, 3. At time pi, I'm at the point 3, 0. At the time 2 pi, I'm at 0, -3. And then I'm at -3, 0. And then we'll just go ahead and take out our pencil and as carefully as we can draw a really nice circle. Remember, these things have orientation, so we should show the orientation with little arrows on the circle. So find the velocity and acceleration at t equals pi. Well, we just had the velocity vector. It's on the other side of your paper. The velocity vector is 3/2 cosine t over 2 in the horizontal, -3/2 sine t over 2 in the vertical. So I'm going to multiply by vectors I and j respectively. At pi, substituting pi in, I get a vector, and that vector is 0i, which I wouldn't have to necessarily do the 0i. I could just go ahead and not write anything. But it's nice to know with you, just working with vectors, some of you for the first time, that I've got no motion, no velocity, in the horizontal direction. Plus -3/2 j. Now that's what's happening at time pi. So here's what I could do. It said to indicate the velocity vector. My velocity vector at pi is right here. So that's the sum of unit vectors. So this horizontal vector I is stretched horizontally by 0. So in other words, multiply that by 0 and it's going to 0 out. The vertical vector j, which is one unit on the y-axis is being stretched 3/2 and flipped. So in other words, when I add those two vectors together, I get that vector right there. Sweet. However, a little more descriptive if I'm talking about the path, to go ahead and put it at time pi. So at time pi, we are at the ordered pair 3, 0. So I'm going to take this vector, and you found this with the delta math assignment from the other day, that as long as I keep the same motion or the same direction and same length, it's the same vector. So instead of putting it in standard position, I'm going to go ahead and put it over here at 3, 0, which is the position at pi. You might have been on a Ferris wheel, or a merry-go-round at the park. And, one of the ones you sit in and somebody runs around and around and around, and people invariably fly off. I may or may not have dove to catch my niece who flew off to keep her from then being sucked under the, and then, yeah, that would have been bad. So, pretty much saved her life. No big deal. But if we're picturing a Ferris wheel, a merry-go-round, pardon me, we're picturing a merry-go-round, and this thing's going around and around and around and around. What that means is that at this point, you let go, you're going to kind of be thrown in that direction right there. You'll have 0 horizontal velocity, and you're just going to fly off and go in that direction. That's what that vector means right there. Now let's look at the acceleration. The acceleration vector is the derivative of velocity, and maybe I'll even indicate that if you're taking notes at home, v prime of t. We found it on the previous page. 3/4 sine t over 2 in the horizontal, negative 3/4 cosine of t over 2 in the vertical. That's what we found on the previous page. Substitute pi in, and we ended up with sine of pi over 2 is 1, negative 3/4 times vector I. I'm going to zero out the vertical component, so I just get negative 3/4 I. In standard position, that vector would be this. It's the unit vector on the x-axis, unit meaning one length, or length of 1, flipped and compressed to a length of 3/4. I'm going to now slide that over to be right there. Hopefully, if you've had physics before and you've thought of that conundrum about centripetal and centrifugal, that negative 3/4 in the horizontal direction only is going to lead to a centripetal force, not the centrifugal force. The centripetal force is the force that's pulling the object inside. So there you go. Supports what maybe you learned in physics. Questions? Go ahead and do example 2. I'll walk around as you do it, and then we'll discuss the answer real quick. So go ahead. I made a TXY table. I chose some values in the domain for t that gave me reasonable values in the range for x and y. I got the sideways opening parabola. We did that problem last week with, like I said, t squared minus 4. We did the same problem. So I got the sideways opening parabola. When I graphed the top opening parabola, when I did 0, 1, 2, 3, I decided, let's go ahead and see the other half of it by substituting in negative time values. Notice I do have the arrows indicating the direction of motion. Now let's go ahead and find the derivative. When I take the derivative of t squared minus 3, the horizontal component, I get 2t And when I take the derivative of tj, the derivative of t with respect to t is 1, so I get 1j. So that's how I got my velocity vector. And notice you have to indicate that it's a vector by saying times vector I and times vector j, or put it in component form. So I could have written this way, indicating that it's a vector function. Its output is a vector, like that. Now, at time 0, when I substitute 0 in for t, I get 0 for the horizontal component, but I get 1 for the vertical component. And so I get just the vector 0, I plus 1j. That's at time 0. So there's 0i plus 1j. And rather than draw it at the origin and standard position, let's draw it at the position. The position at time 0 was -3, 0. So that's why I drew it over here. At time 2, if I stick with velocity, at time 2, substituting 2 in for t gives me 2 times 2 is 4. There's no variable, and I have a constant acceleration in the vertical direction. So it's the vector 4, 1. The vector 4, 1 looks like this. 4, 1 is the tip of the vector. In standard position, it would look like that. If I want to translate it to that point at time 2, the ordered pair is 1, 2, and that's why I translated the vector there. Looking at the acceleration, I just have to take the derivative of the horizontal component, multiply by I, take the derivative of the vertical component, and multiply by j. So the derivative of 2t is 2. The derivative of 1j with respect to t, the derivative of 1 is 0, so that's why we've got oj. At time 0, the acceleration is 2i. At time 2, the acceleration is 2i. At any time, the acceleration is 2i, which means we have constant acceleration. And from the position at time 0, draw in that 2i. From the position at time 2, draw in the vector 2i. Questions? Yes? Yeah. The speed. So let's find the speed. The speed at time 0. All right. So the speed at time 0 is going to be 2 squared plus 1 squared. And take the square root. So substitute 0. Take the horizontal component of the velocity. Oops. Which is 0. Take the vertical component, square it, and take the square root. So in other words, the speed is 1. At time 2, take the horizontal component of the velocity squared plus the vertical component of velocity squared, and we get the square root of 17. Next problem. So when we found the speed before, it was really satisfying. It simplified to 3/2, and it was just kind of cool because we got to factor out, take the square root, and we got the times 1, and things were hunky. This one is far less satisfying to eliminate the parameter. Go ahead and take a minute, stop listening to me yammer on, and see if you can eliminate the parameter, and just do it off on the side over here. Go ahead and eliminate the parameter. In other words, eliminate the t, and make it y equals something with x in it. Go.
Mr. Law, sometimes when you like write your sine and cosine, you never put the parentheses. And it's like,
George loves lawns.
I never do, or you never do.
oh no, you know, like how much work.
No. I only do it when
Click on my parentheses, what can I say?
I only do it when I need to. So x equals e to the t, which means if I take the natural log of both sides, t equals the natural log of x. So y equals ln t. But instead of ln t, I'm going to say y equals the natural log of, that's like the needle across the record screech to a halt. Instead of t, I'm going to put the natural log of x. So we talked yesterday about what's the domain of this vector valued function. And we know here that t is allowed to be any real number. We know here t has to be a non-negative number greater than 0. I'm sorry, it has to be a positive number greater than 0. We now can look at what the domain of this is going to be. Since I know that t has to be a value that's greater than 0, my x value is going to be greater than 0. Here, the range for y is the range of the natural log function, which is negative infinity to, t has to be greater than 0, so x is going to be greater than e to the t. In other words, x is going to be greater than e to the 0, x is going to be greater than 1. So we do get a vertical asymptote, and the graph looks like this. The graph looks like this. We're going to graph it on the calculator in a second. So let's take out our calculator. Let's graph this puppy. Here's me graphing it in parametric mode. So you need to recognize that if the graph doesn't quote-unquote start at that point right there, that is a vertical asymptote. The natural log is a vertical asymptote. Tie has some limitations, I know. I'm disappointed too. Tie has limitations that there needs to be a pixel or several pixels in order to show that vertical asymptote. But we've already kind of exhausted Tie's pixels to get closer to that vertical asymptote. Since we're looking at the natural log of x, we know that the x value has to be greater than 1 with the work that we just did. So x has to be greater than 1. That's my vertical asymptote. All right, so there we've got our curve. From there, find the velocity and acceleration vectors and the speed at t equals 1. So the velocity vector as a function is the derivative of the position vector. The derivative of e to the t with respect to t is e to the t times the horizontal vector I. The derivative of the natural log of t is 1 over t. So at 1, I get e to the 1 times I. It'd be really nice if the next thing was O, because then I have EI over that. And then I get 1 over 1 times j. We'll draw that vector in a second. The acceleration vector is the derivative of the velocity vector. I get e to the t times the horizontal vector I. I'm going to keep reminding you that I've got to put the times I, because we're going to be inclined to say, oh, I took the derivative, I've got the horizontal component, and we're going to forget that without the I there, it's not a vector, and we have to make sure that we're reminding that it's a vector. The derivative of 1 over t, that's t to the negative 1, so exponent times coefficient, drop the power 1.
Good morning, BT. We are going to begin the severe.
So now we're going to find the acceleration vector at 1 by taking a of 1, and it's going to be e to the 1 times vector I minus 1 over 1 squared times vector j. So if I wanted to sketch those vectors at those times, at the point 1, we see that r of 1 equals e plus ei plus ln 1j. So it's e comma 0 is the position, and yeah, something like that. That's close. So the velocity vector is e in the horizontal and 1 in the vertical. So that would be this vector here in standard position, but I'm going to go ahead and put it on the curve. And then this vector is e minus 1, so e minus 1. That's this vector right here. I'm going to go ahead and put it at the point, and there it is. Let's find the speed. The speed at 1 is the velocity at 1 squared in the horizontal plus the velocity at 1 in the vertical squared. Take the square root, and we get the square root of e squared plus 1 squared. As a decimal, does anybody have that handy?
2.896.
2.896 is the speed at 1. All right. Now, what happens to the position, velocity, and acceleration as t approaches infinity? Remember, we're just going to take limits at infinity. We have to do it in both the horizontal and the vertical direction. So what's going to happen is the position is going to approach e to the infinity plus natural log infinity. So it's going to approach infinity I plus the natural log of infinity j, but it's going to get to infinity horizontally quicker than it does to the vertical. The velocity is going to approach well, when I substitute infinity in here, it's going to approach infinity I plus 1 divided by infinity, 0j, and it's going to approach 0j from above. From above? Oh, all right. If you had me for slant asymptotes last year, we talked about from above and from below. This quantity is approaching 0, but I'm adding that small fraction. So that's why it's decreasing and I'm approaching from above. The acceleration is going to do the same thing, but it's going to do it from below. So it's going to approach 0, j, but it's going to do it from below. All right. Let's do an example where we have to work backwards. And working backwards, we have to integrate to go from acceleration to velocity. We have to integrate to go from velocity to position. Each horizontal and vertical component will have the plus c. So I've given you the acceleration vector. The velocity vector is going to equal the acceleration of the the integral of the acceleration vector. So I'm going to integrate I. It's 1 times I, and I'm integrating with respect to t. The antiderivative of 1 with respect to t, like I say, is t. Say it with me, plus c. And there's the horizontal component of the velocity vector. I just integrated 1I. Plus, now I've got to integrate 2j. When I integrate 2j, with respect to t, it's 2t plus c2 times vector j. And now we're going to find c1 and c2. Ooh. I don't see enough numbers.
Starts at rest.
It starts at rest, so that tells us the 3 numbers. What are the 3 numbers? Adam, what are the 3 numbers?
I don't know. 0, so it's C1 0.
Well, okay, you're jumping ahead to solving. We'll back up 1. So t equals 0, because that's starting. Okay, it starts at rest, so that's telling me t equals 0. And at rest means that the horizontal component is equal to 0, and the vertical component is equal to 0. I don't know the best notation for that. So in other words, I'm going to set 0 plus c1 equal to 0, and I now know c1 equals 0. 2 times 0 plus c2 equals 0, so I know c2 equals 0. So I now have that my velocity vector is equal to ti plus 2tj. Remember, I'm just integrating the function, the coefficient on I with respect to t, and then multiplying by I. I'm integrating the coefficient on j and then multiplying by j. So the position vector is the integral of the velocity vector with respect to t. So in other words, I'm going to integrate that ti plus 2tj raised to the power 1 divided by the new exponent plus c. I don't know, maybe c3. Raised to the power 1 divided by the new exponent. Say it with me. Plus c. 4. And now I've got the 3 numbers. That is very explosive. The 3 numbers are at t equals 0, the horizontal is -1 and the vertical is 2. So 1/2 0 squared plus c3 equals -1. So now I know c3 equals -1. 0 squared plus c4 equals 2. So now I know C4 is 2. So now I've got my position vector. My position vector is 1/2 t squared minus 1 in the horizontal, so times vector I, plus t squared plus 2 in the vector, or in the vertical, so times vector j. And then we'll go ahead and finish her off by substituting 2 in. So now I know that the position at 2 is 0i. Oh, nope, sorry. 4 divided by 2 is 2. 2 minus 1 is 1i. Plus 6j. So in other words, the position is at 1,6. Bueno? So that initial tells me times 0 again.
I honestly didn't read so.
And it gives me a velocity vector. It's not starting at rest in this case. So I'm going to use 1 and 1 to solve for the plus c on the velocity integration, and then use 1 and 1 again for the position. So let's see, velocity is going to equal the antiderivative of negative cosine t times I is going to be negative sine times t plus c plus negative cosine t, that's the antiderivative of sine, is negative cosine, yay flashcard packs, plus c times j. I just integrated the position. Okay, I integrated the acceleration. Negative sign, initial means 0, plus c gives us 1, because that was the coefficient on I. Okay, so that's where I got the 1 from. Yay? Coefficient on I. So now I know c equals 1, because the sine of 0 is 0. Negative cosine 0 plus c equals 1. And I got that from the 1j. That's how I got that one. So I now know that c equals 2. So I've got my velocity vector. And for Tebrase's sake, there are my parentheses. I would always put parentheses there.
Yeah, because that one you
I need it. And it's wrong with the capital R not to. And then we would integrate again. To get the position. The antiderivative of negative sine t. Cosine t. The antiderivative of 1. Say it with me. Plus c. Because the antiderivative of sine is negative cosine. The opposite of negative cosine is positive cosine. The antiderivative of 1 is t. The vertical component, the antiderivative of negative cosine is negative sine. Plus 2t, say it with me, plus c. And now I'm going to find that value of c using the 1 and 1 from the initial position. At time 0, cosine of 0 is 1, plus time 0 plus c equals 1, and that 1 right there is coming from that 1 right there. Negative sine 0 plus 2 times 0 plus c equals 1. And that 1 is coming from that 1. So we get that r of t is equal to cosine t plus t. This c1 over here is equal to, cosine of 0 is 1, subtract 1 from both sides, I get plus 0. When I substitute 0 in there, I get negative 1, add 1 to both sides, and I get 2. And there's the r of t. Question? What is 1, negative 1, add 1 to both sides to get c by itself?
Sine of 0 is 1.
Sine of 0 is 0. Yep, thank you. That should be 1. C equals 1 then. Thanks. Thanks.